Following are the precedence requirements, normal and crash activity times, and normal and crash costs for a construction project. So we have been given the various activities of the project. We have also been given the relationship between these activities in the form of preceding activities for each of the activity. We have also been given the normal time taken for each activity to be completed. So this can be based on the single estimate of the activity or the PERT formula, which is TO plus 4 times TM plus TP divided by 6. TO is the optimistic time, the TM is the most likely time, and TP is the pessimistic time. We have also been given the crash time, which is the minimum time required to complete the activity even after deploying additional resources. Now, for the normal time, the normal cost is $10,000 for activity A, whereas after crashing, the cost of performing the activity is $11,000. So let's understand this in detail. So let's say we have one resource who's working on this activity, and let's say this is the time scale. So this is 1, 2, 3, and 4 weeks. So with one resource, it takes 4 weeks to complete this activity. Now for crashing, we are using another resource in parallel. So both of these resources are working on this activity. Now let's say for one resource, the cost of using that resource is $2,500 per week. So for 4 weeks, the total cost is $10,000 for 4 weeks. Now, by using two resources, we are able to reduce the overall completion time to 2 weeks. So for this 2 weeks, the cost of the first resource is going to be $5,000. And suppose for this resource also, the cost is $2,500 per week. So for 2 weeks, the cost is going to be $5,000. So the total cost of both these resources for 2 weeks will be $10,000. Now, while we are using the second resource also in parallel, there may be some additional overhead costs. For example, we'll have to have a second laptop for the second resource. There may be additional costs along with that. So the additional costs have been evaluated to be $1,000. So the total cost of completing the activity in 2 weeks has been given as $11,000. So similarly, we have been given the normal and the crash costs for all the activities. Now for some of the activities like activity E, the crash time is also equal to the normal time. What this means is that it is not possible to crash this activity even by using additional resources. Now we are being asked to find the critical path and the estimated completion time of the project using the normal time required for each of the activities. Also, if we calculate the total time taken by the project using the normal time estimate, it will come to 4 plus 3 7 plus 2 9 plus 5 14 plus 1 15 plus 3 18 plus 4 22 plus 4 26 and plus 6 32. And the crash time is 2 plus 2 4 plus 1 5 plus 3 8 plus 1 9 plus 2 11 plus 2 13 plus 1 14 plus 5 19. So even though we can complete the project in 19 weeks, there is a lot of additional costs that we'll have to incur for reducing the time. But the project management has decided that as long as we can reduce this time by 3 weeks, we may be able to get a better return on the project than by reducing the project by 32 minus 19, that is 13 weeks. So we are being asked that to shorten the project by 3 weeks, which tasks would be shortened and what would be the final total project cost. So I've noted down the information that has been provided to us regarding this project. Now let's try to find out the additional cost per week for each of the activities for crashing it. So for activity A, the cost is $1,000 extra and the crash time is 2 weeks less. So 1000 divided by 2, which is 500. So additional cost per week is $500. For activity B, the difference is $3,000 and the time difference is 1 week. So 3000 divided by 1 is 3000. For C, the additional cost is $2,000 and the reduction in time is 1 week. So 2000 divided by 1 is 2000. For D, the cost difference is $4,000, whereas the time reduction is 2 weeks. So 4000 divided by 2, which is $2,000. For E, there is no reduction in the crash time, nor is there a difference in the normal cost and the crash cost, so cost per week is 0. For F, the cost difference is $1,000 while the time difference is 1 week, so 1000 divided by 1, which is 1000. For G, the cost difference is 25,000 minus 13,000, which is $12,000, while the time difference is 2 weeks, so 12,000 divided by 2, which is 6,000. For H, the cost difference is $7,000 while the time difference is 3 weeks, so 7,000 divided by 3, which is 2,333. For I, the cost difference is $9,000 while the time difference is 1 week, so 9,000 divided by 1, which is 9,000. Now let's find out the weeks to decrease. So 4 minus 2 is 2, 3 minus 2 is 1, 2 minus 1 is 1, 5 minus 3 is 2, 1 minus 1 is 0, 3 minus 2 is 1, 4 minus 2 is 2, 4 minus 1 is 3, and 6 minus 5 is 1. Now the first question for us is to draw the network diagram, find the critical path, and the estimated completion time. So let's first draw the network diagram. So let's say this is the starting node number 1. Now activity A does not have any predecessor, so the starting activity is activity A. So let's draw A. This is the ending node for A. Now B and C are both dependent on the completion of A. So let's draw B and C. Let's say this is B and this is C. So we have completed A, B and C. Now next is D, which is dependent on B, and E, which is dependent on both B and C. So let's say 3 is the ending node for B and 4 is the ending node for C. Now let's first draw D, which is dependent only on B. So let's say this is D. So we have completed D. Now E is dependent on both B and C. while F is dependent on C. So if we draw a dummy activity from 3 to 4 and then draw E from here, that would mean E is dependent on both B and C, which meets this criteria. However, F is dependent only on C. So if we draw F from here as well, then that would mean that F is also dependent on both B and C. So this is not going to work. Now let's say we draw a dummy activity from 4 to 3, and then from 3 we start activity E. So that E would also mean that it is dependent on both B and C. However, that would also mean that D is also dependent on both B and C, because the dummy is coming from 4 to 3. But D is dependent only on B. So what we need to do is to draw a dummy from 3 as well as from 4 and have the ending node here. Let's say this is 5, and from this then we can draw E, and then F is dependent only on C, so from 4 then we can draw F. So we have completed E and F. Now next is G, which is dependent on both E and F. So both E and F. So let me modify this diagram to have both E and F merge into one node, and then from there we can start the activity G. So this is E and this is F, and this will be the ending node. Let's say this is 6, and then from here we can then start G. Now H is dependent on D and E, so D is this and E is this. Now if I draw an activity from here and we have a node here, and then from this node we start H, what that would mean is H is dependent on D, and because of this dummy it is dependent on this node, which is both E and F, but we only want D and E. So what that means is that somehow we'll have to draw E in such a way that E and F are the predecessors for G and E and D are the predecessors for H. So what that means is that if we draw E like this and say this is 6, and then we can draw a dummy here and then a dummy here, what this would mean is G is dependent on both E and F, and H will be dependent on both D and E. So let's modify this diagram and then we'll draw this structure. So what we'll do is from 5 we will draw E, and we'll draw the ending node for E here. Let's say this is 7, and from this node we'll draw a dummy to node 6. So this means G is dependent on both E and F, and that's what we wanted. G is dependent on both E and F. Now what we want to show is H is dependent on both D and E. So we have to draw a dummy from here. So let's do that. And then we'll draw an ending node here. Let's say this is 8. And then from here we'll draw H. So what this means is H is dependent on D and E, and G is dependent on E and F. So we have drawn G and H. Now next is I, which is dependent on both H and G. So H and G have to merge into one node, and then from there we can draw I. So let me modify these two. So let's say this is H, and this is G, and both of them merge into one node. So this is 9, and from here we will have I, and this ends in the finish node, which is 10. So let us validate that the network diagram is accurate. So A doesn't have any predecessor activities, so that's fine. A preceding activity is nil. B and C are dependent on A, so B and C are dependent on A. D is dependent on B, D is dependent only on B. E is dependent on B and C, so E here is, because of these dummy activities, is dependent only on B and C. F is dependent only on C, so F is dependent only on C. G is dependent on E and F, so this is G. G is dependent on E and F because this is a dummy activity. H is dependent on D and E, so H is dependent on D and through this dummy activity on E. And I is dependent on H and G, so I is dependent on H and G. So the diagram looks accurate. Now let's note down the normal time estimate for each of these activities. So A is 4, B is 3, C is 2, D is 5, E is 1, F is 3, H is 4, G is 4, and I is 6. Alright, so with this information, now let's identify the critical path. So let us identify all the possible paths from 1 to 10, and then we'll find out the duration for each of these paths in order to find the critical path. So the first possible path is A, B, D, H, I. So A, B, D, H, I. The next one is A, B, E, H, I. So we have taken the dummy root here like this. So A, B, E, H, I. So A, B, E, H, I. The next one will be A, B, E, G, I. A, B, E, G, I. Alright, so we have exhausted all the paths for A and B combination. Now let's take the A and C combination. So A, C, E, H, I. The next is A, C, E, G, I. The next is A, C, F, G, I. So now let's find out the duration for each of these paths. So the first one is A, B, D, H, I. So 4 plus 3 is 7. 7 plus 5 is 12. 12 plus 4 is 16. 16 plus 6 is 22. So this is 22. Next is A, B, E, H, I. So A, B, E, H, I. So 4 plus 3 is 7. Plus 1 is 8. Plus 4 is 12. Plus 6 is 18. The next one is A, B, E, G, I. So A, B, E, G, I. So 4 plus 3 is 7, plus 1 8, plus 4 12, and plus 6 18. The next one is ACEHI. So ACEHI, 4 plus 2 6 plus 1 7 plus 4 11 plus 6 17. Next is ACEGI. So ACEGI, 4 plus 2 6 plus 1 7 plus 4 11 plus 6 17. And the last one is ACFGI. So ACFGI, so 4 plus 2 6 plus 3 9 plus 4 13 plus 6 19. So the longest path here is ABDHI, which is this path, and the duration is 22 weeks. So the path is A, B, D, H, I. Now the next part of the question is to shorten the project by 3 weeks, which tasks would be shortened and what would the final total project cost be? Now we know that the length of the project is the same as the length of the critical path. So in order to shorten the duration of the project, we have to shorten the duration of the activities on the critical path. Now there may be a possibility that there are 2 critical paths, but in this case we have only one critical path, which is ABDHI. So we have to shorten the duration of one of the tasks on this critical path. Now once we have identified that, now we need to identify out of these critical activities which activity has the least cost of shortening it. So let's look at the cost per week for crashing the critical activities. So the critical activities are A, B, D, H, and I. So out of these costs, the cheapest is activity A, which is $500. So first week activity A, $500. So now if we reduce activity A by 1 week, so activity A becomes 3 weeks, and the critical path A, B, D, H, I becomes 21 weeks. So this becomes 21 weeks, which is still the critical path because this is the highest number from the remaining paths. So we have reduced the overall project by 1 week and activity A by 1 week. So from 4 we have brought it down to 3 weeks. But we can further bring it down by another week because the cost per week for activity A is the lowest. So second week also activity A at a cost of $500. So A becomes 2 weeks and A, B, D, H, I becomes 20 weeks. So now we have reduced the duration of the project by 2 weeks, and we have also crashed the activity A to its maximum limit. So crash time is 2 weeks, so we have brought the time from 4 to 2 weeks. So activity A is no longer available for crashing. So now the options are B, D, H, and I. So now again let's find out which is the cheapest activity for crashing. So activity D appears to have the lowest cost per week for crashing, and we can crash it by another 2 weeks. So let's crash activity D by one more week at a cost of $2,000. So the third week will be activity D at a cost of $2,000. So D, the duration becomes 4 weeks instead of 5 weeks, and the critical path A, B, D, H, I becomes 19 weeks. So the first part of the second question was to shorten the project by 3 weeks, which tasks would be shortened? So it is A and D. And the next part is what would be the final total project cost? So let's find that out. So activity A, we have crashed it completely by 2 weeks. So the new cost is $11,000. So new project cost is equal to 11,000. Now for activity B, we didn't do any crashing for this activity, so we'll take the normal cost, which is $6,000. For C, again we didn't do anything, so it's 4,000. For D, we did crash by 1 week, which is an additional cost of $2,000. So 14,000 plus 2,000, which is 16,000. E, we didn't do anything, so 9,000. F, again we didn't do anything, so 7,000. G, we didn't do anything, so 13,000. H, 11,000. And I is again 20,000. So now let's add it up. So 11 plus 6 is 17, 17 plus 4 is 21, 21 plus 16 is 37, 37 plus 9 is 46, 46 plus 7 is 53, 53 plus 13 is 66, 66 plus 11 is 77, 77 plus 20 is 97. So the total cost is $97,000, and this is when we have incurred an additional cost of 500 plus 500 plus 2,000, which is $3,000. So the normal cost was $94,000, and after crashing and reducing the overall project duration by 3 weeks, our cost has increased to $97,000.